All right, so VTune. In the agenda, the session was titled OpenMP Part 2, and then in parentheses VTune. It's more VTune than it is OpenMP, but I'll mention OpenMP a couple of times so that you get the feeling that it's the right session. All right, seen that before? Okay, so I'm going to focus on the user interface. There will be a little bit of command line though. And then we will talk about how you can use VTune in a typical performance run together with MPI, and we will also do OpenMP analysis. And then I will talk about two analysis types, the HPC performance analysis and the memory analysis, that are particularly helpful for a machine like KNL. Okay? Okay, VTune introduction. So the idea of VTune, who has used VTune before? So the amplifier VTune. Okay, who has used the old VTune, like 10 years ago? Okay, good. I really feel sorry about this, that you had to use it. So VTune amplifier is now the new and current VTune product. And what we did is we invested a lot of time in making it pretty and easy to use, right? The old VTune was a great tool, but it was, a massive amount of data that was presented to you, and it was really hard to digest. And then, when you asked the VTune architects at that time, hey, I have a feature request. Can the tool please compute that metric? The answer typically was, don't you have a calculator? You can do it yourself. So that was the attitude of the whole tool, right? And with VTune Amplifier, we tried to fix that so that it becomes actually accessible for, an experienced programmer that is interested in performance. Okay, so, there's a little bit of GUI. You can open and close projects. You have recent projects. You have probably a current project. You can open results. So, it's a bit more accessible in terms of how it looks like. Now, when you are talking about a project, what you will see is two main areas, basically. Here, you select what you want to have analyzed. So, for instance, if you want to get a hotspot profile, that's the one you would use. Or if you want to know how your code behaves on the machine, you would choose something like general exploration. Okay? And then, really easy now, you punch the start button, and then the tool starts up your application. It runs it in the background. It collects performance data, and once it is done, it will present you the performance data. It's really easy, right? It's really for dummy users. The other thing that you can do is, if you configure an analysis, you can ask the tool to get you the command line. And that's the thing you can cut and paste into your job script for Slurm and then run VTune remotely on a cluster node, collecting data there. And then you can copy, as Hans was telling you about 2 hours ago, you can then tar it up to SCP or whatever protocol you're using. You can get it from the remote machine to your local machine, or if you happen to have a laptop that is attached to the shared storage of your cluster, you can immediately access it from the remote file system. Okay? Okay. And then what you'll get is this. Right? And one thing, I'm really trying to get the point across that it's a lot easier to access performance data now. Red means bad, green means good. It's really visual, right? You can just look at the screen and you will immediately see if there's a performance problem. You don't have to take your desk calculator and then divide some billion number against another billion number at this billion number and then get a performance metric out, look at the performance manual of your favorite Intel CPU and see, oh, there's a performance problem. Right? This is all gone. The tool is a lot smarter in presenting that information. So what you get is your hotspots in terms of compute time, wait time, or whatever the metric is you're looking at. Then a color code indicating if you got poor, okay, ideal performance, or in some cases, if it comes to threading, we can even tell you if you oversubscribed the system and if you overloaded the system and you get a performance penalty by oversubscription. Okay? Then it presents a grid of numbers, again, already processed. right? And again, red means there's a potential performance problem. So if one of those cells is highlighted with this red rose color, you know, I'm not into colors. So this is blue. There are probably 1,000 other words for this kind of blue. Here, this red kind of color, it will tell you, okay, in this hotspot, there is a performance problem with regard to that metric, like, for instance, in this case, overhead and spin time. Okay? The other thing you will see is down here, there's a timeline. So for each thread, there is a bar. And over time, VTune shows you what this thread did on the machine. Was it running? Was it even there? So when did you create the thread? Was it running? Was it waiting? Did it execute instructions on the CPU? Did it spin wait? Did it do MPI? Whatever it did, it is recorded on this in this command line. The other thing you will see is if you have a task-based programming model, or also for OpenMP, to go back to the agenda, you will see those brackets in here indicating there was a parallel region that started here on the timeline and it ended here. So it also gives you additional context information about what is going on in terms of the OpenMP programming model. Okay? And then, of course, you can add information to it. So there's a way you can programmatically tell VTune that now the preconditioner of your code starts, the preconditioner ends, and now the solver starts, and it does iterations, and you can have a tick mark on the timeline for each of your iterations in the solver if you want to. Okay? So there's a lot more information that you can also add manually if you want it. Okay, and then, of course, there's the source code view. So if you click on one of those hotspots, VTune takes you to a source code view that breaks the performance data down for each of your lines in your source code, but also for the assembly code. Okay? Now this is all statistics. Okay? So that means if you look at your code, it doesn't necessarily mean that this instruction took really 3.8 seconds, and the next one only 2.5 seconds. You know, there's a statistical fussiness in this performance data, but at least it's a lot more detailed than something like wall clock time that just tells you my code ran for 10 minutes, and that's it. Okay? So take it with a grain of salt. It's not highly accurate, but it's accurate enough so that you can, limit the scope of your performance problem to actually fix it. Okay? All right. Then the other thing that we have is, so anytime you take a lock in your code, what you will see is transitions between your threads telling you why a thread transitioned to another thread. So for instance, it tells you that there was a sync object. In this case, it was the TBB, the threading building block scheduler. And in the object it was syncing on was in task manager TBB CBP line something. Right? And anytime you take a lock, it will tell you which thread caused the waiting on the lock. Right? Who was the thread who was waiting, and who was the owner of the lock when this particular thread started waiting on this lock. Okay, so there's a lot of information that you can get from the tool. And then, okay, you can have frames and user tasks, and you can mark the timeline both by clicking a button on the GUI, but also programmatically from an API that you can call from your code if you wish to. Okay, now, well, we are all parallelism experts, so we don't use locks at all, right? But sometimes you have to. And then what you see is typical behavior, like a coarse grain lock looks like this in the timeline, where you see that you have 4 threads, in this case running, but they are actually running sequential because the lock is too coarse grained. That's probably an issue that Hans was pointing out in CP2K, right? I'm sorry, quantum espresso. All right, quantum espresso. So there the problem was a too coarse grain lock. Here you see that you have a lock that is highly competitive, where people are really contending on the lock usage. And then in the timeline, you can also see something like a load imbalance, where some of the threads finish early and then start waiting, while other threads are either computing more slowly or have more work to do. right? And then you can use VTune to find out if this thread here is a thread that is very busy because it has a lot of work, or if it's just a straggler thread that is working, for instance, on remote memory and therefore is a slow thread. Okay, that's then easier to see because you can then focus on the individual threads. All right, this is now a feature that is, useful or not. That really depends on what you want to do. So basically, what you can do is if you have two results that you collected in VTune, if they are compatible, so two hotspot profiles, for instance, you can compare them. And then the tool tells you the differences. Okay? If that is useful or not, I don't know. It really depends on your usage. It's probably useful if you think about performance regression tests, right? That you can immediately see if over the last integration step you introduce a performance problem into your code. Or you can use it if you did an optimization to get a quick glimpse at, okay, I have a CPU time difference of so much in this hotspot, and if that is solving your performance problem you've been debugging or not. Okay? But don't expect too much out of it, right? It doesn't tell you that your cache behavior is 20% better. It's merely, comparing all the data and doing simple diffs, subtractions. That's all it does. Okay, now this was like the interactive analysis on the same host. What you can also do, Hans already mentioned it to some extent. There is also the possibility to do a remote SSH connection to a remote machine. So I could use my laptop here, launch the VTune GUI, and then run the analysis by clicking a button on my local machine through an SSH tunnel on one of my lab machines in Munich. That would work. On a Cray system, like the TDS that you have here, it depends on the configuration of the Cray system. Usually, if you do run on a Cray system, you cannot SSH into the compute nodes. I don't know, Tim, is this? That was the case, yep. You may do it, or is it? No, you cannot. You cannot. So this doesn't really work. And I don't know. Sometimes there's a package on a Cray system that you can load a module that would allow you to SSH into a node. Talk to your favorite CSCS contact person to see if that is possible or if they can make it available or not. Okay. But anyways, what you then do is you do via SSH host username at host name, you give the application parameter, and whoever configured a Windows shortcut to launch a program will feel comfortable about what you need to give as information. It's basically the application binary path, so where's the executable and what's the name of it, the application parameters, and optional arguments. The working directory. Okay. And then you can click choose analysis, and once you hit an analysis button, an SSH connection goes off to the remote machine. The collector is started there. It collects the performance data and brings it back to your local machine. Okay? Of course, there's overhead to it, right? If you collect like 10, 20 gigabytes of performance data, it takes a little while until the 10 gigabytes are transferred over SSH. All right? So again, be sure that you know what you're doing. Okay. Now, OpenMP, there you go. If you tell VTune to look out for OpenMP parallel programs, okay, that's a small tick mark that you can set. It basically takes additional context information from the OpenMP runtime and adds it to your performance profile. So what it tells you is, for instance, you get an OpenMP analysis. The collection time was like 14 seconds. It will tell you how much serial time you have. So that's everything that is outside a parallel region. And that basically, if you know Amdahl's law and so forth, this kind of gives you already, it's 27%. So the maximum speed up that you can get from that program is what? 3, exactly. There you go. Well, a little more than 3, but close. It also tells you how much time you spent in parallel regions. It also tries to estimate from load imbalances, spin weighting, whatever misbehaviors of the OpenMP code, what the estimated ideal time of your parallel code would be. And what you can see here is that the tool predicts that it can get something like 3.3 seconds out of 10 seconds gained by removing some of those OpenMP bottlenecks. Okay, so that's something that's really interesting. You can do that yourself by collecting timers and everything, but it's a lot easier to get the tool to report that for you. The other thing that it also does is it not only lists hotspots in terms of functions or loops, it also lists hotspots in terms of OpenMP regions, individual OpenMP regions in your code. And it tells you, what is the parallel region, including where it is in your code, and it tells you what is the potential gain and how long it took to execute that parallel region. Right, and then you can focus on the low-hanging fruit in terms of OpenMP optimization. Okay, so you don't have to optimize all your OpenMP regions. You can focus on the ones where you can actually get benefit out of it. Okay, that all is in the summary pane. And then if you add MPI to the equation, and again, let me repeat this to make it crystal clear. VTune is not an MPI analyzer. Okay? It doesn't analyze the MPI traffic. It only understands enough of MPI so that it can tell you a couple of metrics regarding the local node that you're looking at. Okay? It's not analyzing the overall MPI parallelization. That's where Scalaska, Wampir, Intel Trace Analyzer and Collector, CrayPad, and all those MPI analyzers play, right? This is just barely enough so that you can get some useful information about of how your threading and your processor interacted with the MPI part of your code. Okay? So what you can see is it can present information about the local ranks, so the ranks on the local machine of your local node. And it can tell you how much MPI communication time you had in terms of how long the cores were waiting for MPI traffic to come in. Okay? It doesn't tell where the traffic was coming from. It's just the information that you have been waiting, like in this case, 6 seconds or 23% of your time you've been waiting for MPI. Okay? And then you can use something like Vampire or ITech to analyze why you've been waiting so long. Or you can, overlap some other computation with the waiting time or whatever you want to do, right? But at least you get that information out of the system. Okay, and it also can tell you what is the MPI, the OpenMP potential gain. This only works for Intel MPI as far as I know. That's the only MPI that we can detect. Okay. Okay, and the other thing that you will get is, if you turn on MPI analysis, you get those yellow color added to the CPU timeline. And what you will see is, okay, now we don't resolve the individual threads anymore. What you see is like a pattern map, really like 10,000 feet bird's eye view on what your threads on the systems are doing, right? And again, green means they're running. Yellow means that they're communicating. Okay, and then you can see for all your 200-something, 64 threads, 256 threads, whatever you have, you can see if there is a zigzag pattern, or if it's kind of a lockstep pattern, like compute MPI, compute MPI, compute MPI. So you can see that, and in the CPU timeline, you can see when MPI is interjecting your OpenMP threading, is doing something like waiting, or when MPI communication actually occurs. Okay, and as you can see, this seems to be like an iterative solver where every once in a while, in a regular pattern, MPI kicks in, does something, and then the threads run again. Okay, does it make sense? Good. Okie dokie. Yeah, well, that's something you can read up. Okay, now how does the tool compute that? Well, you know, at some point there's a fork where OpenMP starts the OpenMP threads, and by starting means either really physically starting them in the system or waking them up from some sort of sleep state. Okay, so this is basically where the single-threaded master execution changes to be a parallel execution in OpenMP. That's the fork point. Okay, and then green means that this is effective time, so this means that the thread is actually active and creates samples. Then we have imbalance time where the thread is finished and is already in the final state, so sleeping again or terminated. Then we have red parts where a thread is spin waiting on something like a lock or spin waiting to retrieve a task from a task queue, whatever. Scheduling, that is now, for instance, if you do OpenMP schedules dynamic, the tool can actually detect that there's scheduling overhead associated with handing out loop iterations to threads. That's yellow. Gray is the work creation. We can identify atomics, and we can identify reductions. So you can now break down the performance of your individual threads in the individual contributions and relate that to the OpenMP feature that you see in your syntax in Fortran or in C. Right? And then you can see, for instance, if there's an overly long taking reduction, you can think about doing something about the reduction. Either not do it at all, or use a different reduction algorithm, or whatever. Okay? And ideally, it should look like this, right? So everything is green, everybody finishes at the same time. There's only just a little bit of spinning, blah, 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 blah. And what the tool basically does is to estimate that. It moves all that, right, to the end of the parallel region, and then says, we just cut it off. And that is the effective gain that the tool predicts, right, if all the overheads were gone. For instance, all the MPI analyzers have a similar feature. They can simulate an ideal network. So that means zero latency, infinite bandwidth, right? And then your MPI traffic is gone from the equation. It doesn't take any time anymore. And then you can clearly expose load imbalances from the algorithm. Same idea here, basically, right? By simulating that these guys here are idealized, so zero, okay? All right, well, and then of course you can again have this, this grid view where again for each parallel region in your code, the tool tells you what is the imbalance, so how much of runtime, CPU time you lose because imbalances in work, and it also calls it out as percentages, and it also tries to tell you and predict what is the potential gain in terms of when you remove that bottleneck. And the same thing you can have for dynamic scheduling, for instance. So here we have something that is dynamically scheduled. So we have 3 seconds, 3 CPU seconds are just being spent for handing out iterations from the central task queue to the individual worker threads. And that's probably out of 11 seconds, right? So 25% in this case. Oh, there it is. 25%. Okay. The other thing that you can do is barrier-to-barrier time. So sometimes, well, not sometimes. Ideally, you should have something like create parallel region, and then do something in parallel, and then you have a barrier, for instance, to do MPI communication, right? Then potentially the master thread does something like the MPI communication I was mentioning, and then you start an OpenMP4. Okay? So we have a barrier here, that's an explicit barrier. We have a barrier here, and we have another barrier here. Right? And what VTune allows you to do is it understands so-called subregions. And a subregion is from barrier to the next barrier, from one barrier to the next one. So here the region starts, and then the first subregion is the first user barrier, so that one. Then there's another subregion that we can call out here. that's this OpenMP single statement. Here's another barrier. And then the 4, that's the next subregion. And the tool really tries to break down those individual subregions and present them to you as individual regions so that you can optimize also on the subregion level. Okay, this is how it looks like. So you can choose OpenMP barrier to barrier segment as the view that you want to have presented, and then it tells you loop barrier segment 1, segment, and then starts calling out all those subregions so that you can individually analyze them and see if a region has a load imbalance, but this load imbalance may come from one of its segments or subregions. Okay? Yep. Okay. What else? And then serials. So you can also, when you find out that you have some serial fraction in your code, you can explicitly tell the tool to list all serial code shows up as an OpenMP region, okay, as a pseudo region, and then you can see what is contributing to your serial fraction, and then potentially focus on parallelizing those parts or speeding them up by sequential optimizations or whatever. Okay. So one of the things you might look at is if you have VTune and APS allows you to analyze storage traffic. So if you find that you have a lot of serial I/O, then it might be a good idea to switch to the parallel file system and do MPI I/O or parallel file I/O. Okay. Okay. Yeah. Okay, and this is again the scalable timeline I was already showing in one picture. So basically now we abstract away from all the individual threads, but instead we only show like a heat map of what the threads were doing. And again, green means that the thread is running, brown means that the thread is waiting, yellow would show up as MPI traffic, and so forth. And this doesn't give you, it doesn't give you the picture about the individual thread. It's more the overarching view on what the code is doing, right? It's like me looking at the audience, seeing that most of you are still sitting here with open eyes, assuming that you're listening. Okay. Okay, I said that, I think. Yes, and of course, when you click on one of your region hotspot, it directly takes you to the corresponding OpenMP pragma in your code to show you what is going on. All right, make sense? Good. Next thing, typical HPC workflow. This is now practical hands-on type of things that you can try out later at 4, I think, when we have the next hands-on session. Okay, so the idea again, VTune understands just a little bit of MPI, Intel MPI, so that it can present you some first useful metrics. If you want to really analyze MPI traffic, either use the MPI performance snapshot that Hans was presenting this morning, or use Trace Analyzer Collector, Vampire, or any other MPI enabled tool. Okay? The recommended workflow now is, since it is a really bad idea to run the VTune GUI on a KNL compute node. It's a bad idea for several reasons. And the first and foremost is that you can't even log into your compute node. And you can't launch a GUI from a batch script. Okay? So we run the collection with the command line interface on the cluster node. So either if you have direct SSH access to the node, you can reserve the node and run VTune, or you can paste the command line into your job script or your srun, and then run it through the batch system. Okay, and then later on collect the results. Okay, and then we run the report. So this is now, I didn't specifically say it, but it's a post-mortem tool, right? You collect the data and then you analyze it later on. So then you run the report with the GUI, with the graphical user interface on your local machine, like your workstation, your laptop, or if you have somewhat capable login nodes and the local policies allow that, some users also run the VTune GUI through X forwarding on the front-end node of a cluster. It really depends on what is allowed and what the policies are. Okay? Yes, and Hans was saying that just a little bit. The binary format, and this is also in contrast to the old VTune, the current VTune allows you to simply transfer the directory where the results are stored. You don't have to export them, you don't have to pack them or do whatever post-processing with them. You can just SCP the whole folder that VTune created to your local workstation. You copy the binary code and your source code with it, and then you can just open a Linux result on a macOS machine or a Windows machine. Okay, so we really took great care that this workflow now is a little smoother than with the old VTune. Okay, now this is, I said I don't want to bother you with too much of application command lines, but basically I'm going to show you just a little bit how it interacts with MPI. Okay, so again, VTune is an analyzer for a single node. Okay, and what you can do is you now have different ways of running the tool, right? One of the decisions you want to make is, do I want to sample only one particular node of my cluster run, assuming that this single node is a poster child for all the other nodes? Or what you can do is you can run as many VTunes as you run on cluster nodes, but then you may end up with 163 individual result databases that you need to look at. Okay? Yes?
There is also, it's unfortunately an MPI run extension. I think there is this G tool.
I'm coming to that. Don't steal my thunder, sir. I'm trying to build tension here. I want to have a flow in my presentations, and you're disturbing it all. Come on. Okay, so when you do the following, you run amplifier XE with all the command line arguments that I didn't show you so far. I'm just presenting a couple of them, like collecting advanced hotspots into result_dir, and then your application is MPI run -np48, and then your MPI command line. This means on the local node, start VTune. VTune starts the MPI run. MPI run starts your application, and VTune through MPI run attaches to your code on a single node only. Okay? The other thing that you can do is you can turn it around. Now I'm using uprun just to show you something grayish. So you can also do uprun or srun if you want. Okay? And then run 48 ppin16 amplifier CLs, collect hotspots into result dir with MPI app. That's now different. Now we are running 48 of these guys, right? 48 instances of the tool, 16 on each node, and what you will get is 4 result directories, 1 for host name, 1 for the first node, 1 for the second node, and 1 for the third node, and each of the results will collect the performance results of 16 of your MPI ranks. All right? Do you see the difference? Yep. So here, there's only one VTune running, monitoring the local node, and whatever MPI ranks are running on that local node are monitored. And here, we get, as many nodes as you have been working on result directories containing the performance data of this corresponding local node. Okay? Make sense? Now the G tool thing. The other thing that you can do, if you don't want to collect 163 individual result databases, could be just a little bit cumbersome to look at. Okay? What you can do is you can use either way, so either the G tool syntax or some other interesting syntax of MPI run to say something like this. Dear, be nice to your tool, dear MPI run, please run 1 rank of my MPI application on some node. Colon means I'm now talking about another setting. 1 rank of your MPI application. Please run it with amplifier XE collect hotspots into result dir of my MPI application. And then use another 14 nodes or 14 ranks to run the rest of my 16 ranks. So what it will do is rank 0 is not being collected. Rank 1 is being collected with VTune. Rank, whatever the other ranks are not being collected, 2 to 15. Okay? That's also something you could do. If you know that your, I don't know, your MPI rank 47 is misbehaving, and you want to know why, you can use that syntax. The other thing that you can do is, and that's now Intel MPI syntax, there's gtool. So you can tell MPI to run some of the ranks under a tool. And here we use ampl xe blah, 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 the command line again, and then colon, and then a specification of which rank this tool should be attached to. In this case, it's only rank 1. And there you can use the whole beauty of specifications. So you can use something like 1,5-7, 16, 42 to 58, whatever you're interested in. And then the tool will only be attached to those MPI ranks that correspond to this specification here. Okay? Does that sound complicated? No, not at all. But it is complicated. To make this right, it's rather, you need to know what you're doing. Okay, let me talk about HPC performance analysis. Who does HPC in this room? Wow, you're still alive and following my voice. Good. Okay. Now there's a special analysis called HPC performance. And it basically combines all the useful metrics that you might be interested in as an HPC programmer. Okay? So one thing you can do is either use it -collect HPC performance or select HPC performance characterization from the GUI. Okay? And what it does is it basically tells you a couple of key metrics. First of all, of course, elapsed time and the gigaflop rate. And there's a little asterisk to it with a footnote saying metrics are available on hardware that supports floating point PMU events. So that means, oh God, Broadwell, to some very limited extent, KNL, Haswell, Ivy Bridge, Sandy Bridge, Knight's Corner, all those don't. Okay? So it's not that many Intel CPUs. And it's especially embarrassing, again, please bleep the next statement from the video, because Cray machines reported that number 30 years ago, and Intel can't do it in the 21st century. Okay? Well, actually, the story is, let me do a little war story here. The fun fact about counting floating point numbers on our machines is that we actually count floating point numbers. But we count different floating point numbers than what the people expect. We count floating point operations that have been issued for execution, but that have not yet been retired. So that means if you have a branchy code that causes branch mispredicts, you're overcounting. Okay? If you have a non-branchy code, the number is actually pretty accurate. Anyways, okay. 3 performance aspects are reported. CPU utilization, so that means how well you utilize the individual cores of your system. If your application is memory bound, or the memory boundness in a percentage of how much your code is memory bound. And then again, the FPU utilization, giving you some indication whether or not you're using the FPU well or not. Okay, this looks like this. So how do you like this code? 20% CPU utilization, 50% memory bound, FPU utilization 4%. Sounds like the typical sparse code, right? Like a CFD solution on a sparse grid. Okay, now you can break that down, right? You can get more insight into that. So the CPU utilization, it again tells you about how many of your, in this case, 24 logical CPUs you used. So this boils down to 4.5 of them on average. It tells you Again, some OpenMP metrics about how much time you spend in a parallel region. It tells you the estimated ideal time and the OpenMP potential gain. So there's a lot of meat in the OpenMP parallelization in this particular code. And of course, it also tells you about the CPU usage histogram, where you can see that this is what you would like to have, and this is what you got. Okay, so very visual. Okay? And if you're writing a paper about scaling runs on a single node, you can just run VTune and save yourself from computing the speedup factors, because that's exactly your speedup factor here, whatever, 4.5. Okay. All right, memory bound. So what it tells you is how much cycles, right, in the execution pipeline are going into memory accesses. Basically, that is a metric, it is how much cycles are lost because you're waiting for the memory, okay? It tells you if your code is cache or DRAM bound. It tells you for a NUMA system the number of remote accesses that are coming from a remote NUMA socket. And it also shows you a bandwidth utilization histogram so that you can see if you're maxing out the memory bandwidth, first of all, and if you do that all the time. And when you look at real applications, there are spikes in the memory bandwidth usage just to drop down to almost 0, and then it goes up again. Right? And then you can look at those drops to see what the code is doing while it is not using all the memory bandwidth that is available, and then you can potentially change your algorithm so that it does. Okay? Okay, floating point operations. So it tells you the FPU load. So 100% means that you're fully vectorizing, you're using all the FPU cycles in the system. It tells you the chief flops, with a typo, broken down by scalar and packed. So that means floating point operations that come from scalar code versus vectorized floating point code. It tells you the top five loops and functions. It tells you whether or not you're using non-vectorized instructions with a legacy instruction set. And it also gives you some indication whether or not you have memory-bound loops that are not really benefiting from SIMD vectorization. We had a similar question earlier in the OpenMP SIMD talk, where if you have a really memory-bound loop, then the benefit from vectorization is rather low and limited. Okay? And this is how it looks like. Again, grid view. Red means you've got a potential problem. So here, that's again your OpenMP loops, your OpenMP regions, your hotspots, or whatever you ask the tool to present to you. And then it tells you the potential gain. It tells you whether or not you're running out of the L1, L2, L3 cache, whether or not you're DRAM bound, whether you have other accesses, the number of NUMA accesses, how many of them are coming from a remote socket, and the FPU utilization. And you can see this is a bad example for a NUMA code. 50% of the accesses are remote, which means likely somebody allocated all the memory in the local NUMA domain and went out across the whole machine. And so you have every second memory access is a remote access. Okay, memory and yes.
How much of these features are dependent on you having a Broadwell chip?
These, none, because well, apart from L3, of course, right? KNL doesn't have an L3 cache. For KNL, the tool should report DRAM bandwidth and MCDRAM usage, right? I think it doesn't report NUMA traffic though, because it's a single socket, and I'm not sure if that also works with sub-NUMA clustering. But it's not really dependent. The only thing that is really dependent on the machine you're running on is this one, the FPU utilization. On Broadwell, you get more numbers and more accurate numbers than you would get on a Haswell or on a KNL, right? Because the counters are simply not there.
Okay, and I think the PISDANE, just the XC50 partition, this is Haswell, right? These nodes? Sorry?
It's Ivy Bridge.
Yeah, as well, and Broadwell.
Oh,
But Broadwell's the
Broadwell?
XC40, isn't it?
XC50. Yeah.
Yeah.
Okay, which part? the GPU part is Haswell.
Right, yeah. Okay, thanks.
Okay. Memory analysis. That's the other thing that you'll be interested in, likely. Okay. So what you want to know is, when you know that your L1, L2, last level cache, DRAM bound, whatever bound, memory bound, you want to know why. Well, usually you would like to know, I think, right? Now the problem is, you got like your 10 arrays, and the question is, which one of those 10 arrays is the one that is actually memory bound, right? So this is where the memory access collection comes into play, okay? This guy now looks at, again, similar metrics as the SPHPC performance analysis. So it tells you roughly the same things about being L1, L2, L3, or DRAM bound. But it breaks down those numbers into loads and stores. So you can see if your memory traffic is more coming from reads from the memory or writes to the memory. And it also tells you, like, average latencies and so forth for the individual cache levels, okay? The other thing that it shows you is, again, a histogram that shows you for how long, so that's runtime or compute time, you've been in which memory bandwidth bucket. So for instance, for, let's say, almost a second, so 1,000 milliseconds, you've been executing with less than 10 gigabytes per second, okay? So this is a rather low memory bandwidth when you think about a DRAM system that should deliver something like 60 gigabytes per second memory bandwidth on a socket, right? So you can see, how much of memory bandwidth you actually utilize and for how long. The other thing that it shows you is the bandwidth utilization over time. And this is what I was saying about 5 minutes ago, where you have the individual packages, right? The individual links between the packages. So this is now not a KNL picture, this is a Xeon picture, right? So you have package 0 and package 1, two sockets and NUMA domains in your system, and then the two links between the packages. And then you can see of how much of total memory bandwidth per package you've been consuming. And what you can see here is that you likely have a bad NUMA problem, because most traffic is on package 0, whereas package 1 is almost having no memory traffic. Okay? At the same time, what you can see is that from package 1, link 1 and 0 are really maxing out on memory bandwidth. Okay? And that this is an indication for a NUMA problem. Right? And given that, you can find phases in your code where you probably have good NUMA behavior, right? And then all of a sudden, for instance, one of the packages breaks down in memory bandwidth, and the link bandwidth goes up, and then you can focus on that point where this code transitions from the first phase to the second to find out why you're now having a NUMA problem. Do you need to rebalance your data? Do you need to change your algorithm? Whatever. Okay? That's why the timeline view is so important. And of course, you can see incoming and outgoing data, so that is reads and writes and any other traffic like snooping traffic, so you can see, if you have high administrative traffic on the individual QPI links. All right, what else? The other thing that is important, you can ask VTune to not only monitor the memory traffic, but also relate that performance data with the individual data structures. So what it does is it intercepts the most commonly used memory allocation interfaces. So malloc, JE-malloc, TBB-malloc, some of the most commonly used, I think. And then it tells you for each load and store operation, basically it tries to monitor those. And then it tells you that so much traffic was attributed to this data structure, and it tries to find the allocation site for you. So basically, if it's a dynamic allocation, it will tell you that in line 109, you allocated 30 megabytes of data. Okay? Or if it's a global variable, it will tell you that in alloc test G data, there's 300 megabytes of global data in the data segment. Or if it's on the stack, there's a implicit allocation arena called stack. We cannot detect each and every variable, but at least we can relate it to dynamically allocated, static allocated, and stack allocated stuff. Okay, better than nothing. Okay, and then what it tells you is exactly what you're interested in. At least I hope so. It tells you that for the memory object that has been allocated in line 104 with 61 megabytes, you have 42% miscount on the last level cache. And then you can look at this data structure. You know what it is, right? You don't have to investigate the memory traffic for all of your 100 data structures. You can focus on the ones that VTune picks out for you and says, these are the top 4 or 5 of allocations where you're having most of the last level cache misses, right? And then you can focus on those data structures to improve locality on them, whatever, right? And then, the fun starts in getting this fixed, okay? That's another view, again, together with a timeline, the memory allocations and their L2 miscount. You can see, high miscount coming from DRAM traffic, why that is, which data structures are causing them, how big they are, and where they're coming from. Okay? The other thing that you can do with that analysis on a Xeon is you can try to find if this is a good HBM candidate. Right? Because this is a data structure that is causing a lot of cache misses. So you should probably do that optimization and move that data structure into the MCDRAM so that you still get the last level cache misses. Well, in this case, L2 cache misses. But at least you can get the data into the caches with a lot higher bandwidth than from the DRAM. Data structures that are in this low category that almost cause no cache misses, they can still stay in the DRAM, right? If you really need to work from these 16 gigabytes and you have way more data than fits in there. All right. That's it for today. Yeah, free time for me. Questions?
That last part, is it, do you support Fortran?
Yeah, sure. See? Fortran.
So that was a lot of different possibilities. For KNL, realistically, we'll probably be looking at single node codes which have, say, 64 MPI ranks and maybe 2 threads. So what is the proper configuration or proper way to look at that with VTune?
Potentially something like this, right? So you would get a performance profile across your, in this case, 48. Please substitute 64, okay. Right? Or if you have a limited cluster run, you could still do something like this, right? Like if you have, I would say, up to 8 cluster nodes, you can live with the fact that you have like 8 of those individual result files.
So you wouldn't do it this way?
We would do it this way. At least, on a small scale, not across the whole machine. Like on Cori, you wouldn't do that on 9,000 KNL nodes, right?
One node.
Exactly. 1 node or 4 nodes, maybe 8. So something where you have a realistic chance of clicking through the result databases, right? And usually what you would do is, since the MPI traffic needs to be analyzed in a different tool, you would focus on what we call single node performance, right? So you would do an HPC characterization. You would probably also use Advisor to find out if you have a vectorization issue. You would use something like this HPC performance analysis to find out, let me see, let's take this picture. What is the boundness on different levels of the memory hierarchy? You would run a memory analysis to see how much of working set do I have, because that also helps you decide whether or not you want to run your machine in cache mode, or if you need to run the machine in flat mode with the memory analysis telling you which are the hot data structures that you need to move from DRAM into MCDRAM manually, right? Or if you want to use cache mode, do you have data structures that are big enough or bigger than the MCDRAM, but that you can potentially block for 16 gigabyte blocks so that they can still fit into the MCDRAM, right? But that is all something that you can do on a very small scale, assuming that you have a benchmark that is realistic enough, right?
So for this one node example, you have 64 MPI ranks
Mm-hmm.
and 2 threads. 64 MPI ranks and 2 threads, and assuming there's no great load imbalance in the MPI ranks, VTune is going to give you sensible results for
Yes.
those 2
Yes.
OpenMP threads.
Yes. And but that also means that you need to, also analyze the MPI traffic if there is an imbalance in the MPI.
But assuming there's none.
If there is none, then this will give you interesting results, yes.
I have one question.
Sure.
So you've been presenting VTune. There is Advisor as another tool, and ITAC.
Uh-huh.
Will there be a convergence of all those tools?
No, it's not planned right now because the scope is completely different, right? So there's a whiteboard. So we used to have a slide that went like this. So we had a circle, right? There was Advisor, Inspector, Ample, and the Composer. Sometimes, depending on who you ask, these two were interchanged. Okay? So Composer is the compiler product. Advisor is the tool we saw yesterday that gives you, performance advice on threading and SIMD. Inspector is the correctness tool that tells you if you have threading issues like race conditions. And then Amplifier is the performance tool where you can find out about misbehaving code on the machine. Right? And you would take this, and ITAC to some extent is also a performance tool. Although it can do correctness checking as well, but it's meant to be a performance tool. And so you got this cycle. You start with the Intel compiler, with the Intel libraries. You run it through Advisor. It will tell you what are the opportunities. You can use Inspector to debug your code, and then you go for Amplifier for the rest of the performance equation, right? And then you repeat that cycle. And so in this scenario, this is more like an expert tool that helps you develop code, not in the sense that it's an expert tool that you need to be an expert, but the tool is the expert, right? So it tries to help you, make a decision on how you want to move forward with your code. Whereas here, we are assuming that we already have high-performance code, and we want to know how the high-performance code behaves on the machine, right? And since these tools have all different aspects, they are likely going to be separate tools, right? Because the focus of the tool is completely different. There are always things to be added. So, there are new features that we plan for Advisor. There are new things that we are adding to Amplifier. And one of the things we did in the recent past was at least give it some notion of MPI, right? But we will not likely not make it an MPI tool that also can analyze the MPI traffic. Right? That's not what it's meant for. Right? But there's always some little overlap, right? So Advisor uses some technology from Amplifier to do some performance predictions. ITAC can collect a limited amount of performance monitoring unit data, whereas Amplifier just understands a little bit of MPI. So, they're at where they touch each other, it kind of blurs, right? But the kind of analysis that you want to do with the tools is so different that you likely don't want to merge it, right? Not saying that it's not possible, right? Vampire, for instance, or Vampire, is a tool that merges amplifier analysis, offload analysis, MPI analysis, blame shifting, and everything into a single tool. You can do it, but for us, it's, we rather keep those tools simple, or as simple as possible, and separate.
Please correct me if I'm wrong, but Advisor is not yet available for Mac, right?
It is.
It is?
Yes, it is. Well, let me put it this way. Advisor is a tool that is agnostic of KNL or mic. So what you could do, though, I think it started sometime last year, you could actually get a what-if analysis from Advisor saying, what if I had AVX 512 instructions in my code? What would the predicted performance be, right? And you can still do all the analysis in Advisor without even thinking about KNL, right? So, but it runs there, okay? If you want it to run there. There's also a command. I don't know if Heinrich showed it yesterday. I was doing email while he was speaking. I have to admit that. But Advisor also has a command line interface. So you can also run the command line interface on a KNL if you need, the machine. That's supported. If you have a calculator, you can do it yourself. So that was the attitude of the whole tool, right? And with VTune Amplifier, we tried to fix that so that it becomes actually accessible for, an experienced programmer that is interested in performance. Okay, so there's a little bit of GUI. You can open and close projects. You have recent projects. You have probably a current project. You can open results. So it's a bit more accessible in terms of how it looks like. Now, when you are talking about a project, what you will see is two main areas basically. Here, you select what you want to have analyzed. So for instance, if you want to get a hotspot profile, that's the one you would use. Or if you want to know how your code behaves on the machine, you would choose something like general exploration. Okay? And then, really easy now, you punch the start button, and then the tool starts up your application, it runs it in the background, it collects performance data, and once it is done, it will present you the performance data. It's really easy. Right? It's really for dummy users. The other thing that you can do is, if you configure an analysis, you can ask the tool to get you the command line. And that's the thing you can cut and paste into your job script for Slurm, and then run VTune remotely on a cluster node, collecting data there. And then you can copy, as Hans was telling you about 2 hours ago, you can then tar it up, SCP or whatever protocol you're using. You can get it from the remote machine to your local machine, or if you happen to have a laptop that is attached to the shared storage of your cluster, you can immediately really 3.8 seconds, and the next one only 2.5 seconds. There's a statistical fussiness in this performance data, but at least it's a lot more detailed than something like wall clock time that just tells you my code ran for 10 minutes and that's it. Okay, so take it with a grain of salt. It's not highly accurate, but it's accurate enough so that you can, limit the scope of your performance problem to actually fix it. Okay. All right. Then the other thing that we have is, so anytime you take a lock in your code, what you will see is transitions between your threads telling you why a thread transitioned to another thread. So for instance, it tells you that there was a sync object. In this case, it was the TBB, the threading building block scheduler. And in the object it was syncing on was in task manager DBB CBP line something, right? And anytime you take a log, it will tell you which thread caused the waiting on the log, right? Who was the thread who was waiting, and who was the owner of the log when this particular thread started waiting on this log. Okay, so there's a lot of information that you can get from the tool. And then, okay, you can have frames and user tasks, and you can mark the timeline both by clicking a button on the GUI, but also programmatically from an API that you can call from your code if you wish to. Okay, now, well, you know, we are all parallelism experts, so we don't use logs at all, right? But sometimes you have to. And then what you see is typical behavior, like a coarse grain log looks like this in access it from the remote file system. Okay? Okay. And then what you'll get is this, right? And one thing, I'm really trying to get the point across that it's a lot easier to access performance data now. Red means bad, green means good. It's really visual, right? You can just look at the screen and you will immediately see if there's a performance problem. You don't have to take your desk calculator and then divide some billion number against another billion number at this billion number and then get a performance metric out, look at the performance manual of your favorite Intel CPU and see, oh, there's a performance problem. Right? This is all gone. The tool is a lot smarter in presenting that information. So what you get is your hotspots in terms of compute time, wait time, or whatever the metric is you're looking at. Then a color code indicating if you got poor, okay, ideal performance, or in some cases, if it comes to threading, we can even tell you if you oversubscribed the system and if you overloaded the system and you get a performance penalty by oversubscription. Okay? Then it presents a grid of numbers, again, already processed, right? And again, red means there's a potential performance problem. So if one of those cells is highlighted with this red rose color, you know, I'm not into colors. This is blue. There are probably 1,000 other words for this kind of blue. Here, this red kind of color, it will tell you, okay, in this hotspot, there is a performance problem with regard to that metric, like, for instance, in this case, overhead and spin time. Okay? The other thing you will see is down here, there's a timeline. So for each thread, there is a bar. And over time, VTune shows you what this thread did on the machine. Was it running? Was it even there? So when did you create the thread? Was it running? Was it waiting? Did it execute instructions on the CPU? Did it spin wait? Did it do MPI? Whatever it did, it is recorded on in this command line. The other thing you will see is, if you have a task-based programming model, or also for OpenMP, to go back to the agenda, you will see those brackets in here indicating there was a parallel region that started here on the timeline and it ended here. So it also gives you additional context information about what is going on in terms of the OpenMP programming model. Okay? And then, of course, you can add information to it. So there's a way you can programmatically tell VTune that now the preconditioner of your code starts, the preconditioner ends, and now the solver starts, and it does iterations, and you can have a tick mark on the timeline for each of your iterations in the solver if you want to. Okay? So there's a lot more information that you can also add manually if you want it. Okay, and then, of course, there's the source code view. So if you click on one of those hotspots, VTune takes you to a source code view that breaks the performance data down for each of your lines in your source code, but also for the assembly code. Okay? Now this is all statistics. Okay? So that means if you look at your code, it doesn't necessarily mean that this instruction took all right, so VTune. In the agenda, the session was titled OpenMP Part 2, and then in parentheses VTune. It's more VTune than it is OpenMP. But I'll mention OpenMP a couple of times so that you get the feeling that it's the right session. All right, seen that before? Okay, so I'm going to focus on the user interface. There will be a little bit of command line though. And then we will talk about how you can use VTune in a typical performance run together with MPI, and we will also do OpenMP analysis. And then I will talk about two analysis types, the HPC performance analysis and the memory analysis, that are particularly helpful for a machine like KNL. Okay? Okay, VTune introduction. So the idea of VTune, who has used VTune before? So the amplifier VTune. Okay, who has used the old VTune? Like 10 years ago. Okay, good. I really feel sorry about this, that you had to use it. So VTune amplifier is now the new and current VTune product. And what we did is we invested a lot of time in making it pretty and easy to use, right? The old VTune was a great tool, but it was, a massive amount of data that was presented to you, and it was really hard to digest. And then, when you asked the VTune architects at that time, hey, I have a feature request. Can the tool please compute that metric? The answer typically was, don't